Today I wanted to talk how images are made by spherical mirrors and by lenses. Let's start with a spherical mirror. Spherical mirror is a surface which is part of a sphere, and it's it's a relatively small part of a sphere. If we take too large fragment of that sphere, then the surface will not be able to produce image. It will, because of an effect which is referred to as spherical aberration. Really, in order to have mirrors which produce nice images, we would have to make the shape of the surface should be either parabolic, if we want to make an image of an object which is far away, in principle at infinity, and if it is closer, the shape of the surface should be elliptical. However, if I take a tiny fragment of a sphere, then deviation from a parabola or from an ellipsis is very small. Therefore, with a very good approximation, spherical mirrors are able to produce images, and the advantage of spherical mirrors over parabolic or elliptical is that it's easier to make them. They are cheaper to be made. All right, so let's say that here's the center of that spherical surface of the mirror. Halfway between the center of that spherical of the curvature and the center is a point which we refer to as a focal point of a mirror. And in a moment we will see why it is referred to as a what is significant about this point and why is it so important, so that we will have to mark it. Spherical mirror has such a property that if light is coming out from a point, or which in this case it would be a real object, or if light is converging to a point and we place a mirror before the light converges, in this case it's a virtual image, then after the reflection from the surface of the mirror, either the light or the rays of the light or their extension will meet approximately at a point, and that point is the image. Well, the fact that it is meeting approximately is the source of spherical aberration. This is the spherical aberration, that the rays do not exactly meet at a point. All right, so let's now see the illustration. Let's say that we have an object. By the way, if I put a flower in front of the mirror, I will have a real object or a virtual object. Real. And the reason is that the light is coming out from that point. Yes, so rays originate at this point. All right, now, and actually I marked here all the light which is coming out and hitting the mirror. Actually, there is even more light, because we have light coming in this direction, in this direction. Remember that these are the properties of the object which we can see. They have to send light in all directions. So they also send the light in the directions on the surface of the mirror. And here are all the rays which I marked. And if light originated from a point, after it is reflected, it converges to a point. At this point, we will get an image of this point. By the way, the image is going to be real or virtual. Why? What did you say, Oscar? Actually, it is real. the image is real. It is then when extensions meet at a point of the rays. If the rays meet at the point, we have real. So if light is coming out from here, and actually, I mean, if you look at this point over here, there is a light coming from that point in this direction. When we put I over here, we will believe that light is coming out from this point, and actually light is passing through this point. Virtual image would be behind the mirror. Behind the mirror, there's no light coming out from behind the mirror. So then the image is virtual, like in the bathroom mirror. When you look at your face in the mirror, it appears to you that the face is behind the mirror. It is like the light is coming out from behind the mirror. Obviously, it is not. It was reflected at the surface, so the extensions meet at on the other side of the mirror. So this object is also, this image is also real. Well, what we are going to learn today is how to find, how to relate. I mean, if I put an object over here, you will have to find out where the image is formed. And actually, you will have to do the other way around too. If you want to have an image on the screen, you will have to figure out where to put the object for an optical element. Sometimes you will have even a situation that at one location you have object, at one location you have image, and you will have to figure out where to put the optical element in order to get it. All right. It is not possible actually to trace easily any ray. However, 4 of them are easy to trace for a mirror. And if we trace just 2, it will be enough to find an image or whatever we are looking for. Then you can use the remaining 2 to verify if your construction is correct or not. All right. And I want you to learn the names. The book doesn't have those names the same way as I do. But I think that way you will make a better distinction, and it will lead to less confusion. So, well, let's start with this: that the symmetry axis of an optical element is called the principal axis of this element. So here, I consider this mirror and draw a line which is perpendicular to that mirror, and this axis of symmetry. This is principal axis of that mirror. The ray which I mark from the object to the point where the principal axis crosses the mirror is called the chief ray. And I want you also to add word object in front. Object chief ray is the ray which is coming out from the object and hits the mirror. All the rays between the object and the mirror, coming out from the object and hitting the mirror, I want you to add word object in front of it. So here I have object chief ray. Object chief ray has such a property that after it is reflected, it is symmetrical to about the principal axis to the object chief ray, and it is called image chief ray. So object chief ray after reflection becomes image chief ray, and it is symmetrical about principal axis the 2 rays are symmetrical about the principal axis. All right. Now, the ray which passes through the focal point of the mirror, the object ray which passes through the focal point of the mirror is called object focal ray. Object focal ray has such a property that after it is reflected, it travels parallel to the principal axis, and because of that it is called the parallel ray, and because it is now reflected, so it is image parallel ray. So object focal ray after reflection becomes image parallel ray. Now the next one, the ray which passes through the center of curvature, well, obviously it is going to hit the mirror perpendicularly. I mean, the surface of the mirror is going to be perpendicular to the ray, so the ray will be reflected back along the same line. So, and this ray is called normal ray. Normal because it hits the mirror at a zero angle of incidence. It hits perpendicularly. Now, if it happens actually, I mean, in the construction, like over here, it can happen that actually you mark the mirror too small, that normal ray will really never hit the mirror. In this situation, you can just imagine that you can extend that mirror as far as is needed. So think about, well, extending the mirror further. And if you had a mirror, well, actually you will have the surface somewhere over here, so it will be reflected backwards. Fragment of the spherical mirror produces identical, I mean, as long as aberration is not, does not play any significant role, so fragment of the mirror will produce identical image as the entire mirror. So now you can think that this, if the mirror is too small, you can think that it's a fragment of a bigger mirror of the same curvature. And there is one more ray which is easy to trace, and that ray is object parallel ray. So it is parallel to the principal axis, but it is coming out from the object, and it is object parallel ray until it interacts with the optical element. And again here I mean that mirror was too small, so I imagined that this mirror is really a fragment of a bigger mirror of the same properties. So I extend it to this point and say that it would be reflected at this point, and parallel object ray is going to be reflected in such a way that the reflected ray is going to pass through the focal point, and therefore it will be called image focal ray. Okay. Now, if I trace a ray like that, so it hits the mirror over here, can you tell me how it would be reflected by the mirror? Adam has a suggestion. And how about Adam? Why don't you also give a justification? Why do you think that it would be this way?
Just based off of that diagram, the mirror is slanted, tilted, sort of at an angle that it would reflect down.
So it will be reflected down. How about this way?
And the other actual rays that are hit the upper portion, the upper half of the mirror are pointed down, and the ones that hit the lower portion are pointed parallel or up. So.
Well, but I mean, how far down? Yeah, it is
past the halfway. It looks like
yeah,
right at the halfway.
Which way a ray from here would be reflected?
Not totally. Probably like
I mean, is it going to pass through this through here?
Yeah, probably around there.
Like that?
Yeah.
Who agrees with Adam? Anybody disagrees? Mike disagrees, right? Yeah, what's your opinion?
I think the ray will go straight down to the image.
Like this?
Yep.
Why? Who believes Mike? Okay, there is, and Mike is actually right. Yes, well, it is that rays emitted from a point, yeah, they are coming out from this point over here. They have to meet at a point. Yes, so we have to have a point where all rays coming out from this point after being reflected meet. And we have that at this point already 4 rays meet. Well, obviously we cannot have another point then. All of them have to meet over here. So Mike is indeed right. All the rays would meet at the image point. All right. Now I want, okay, and actually this diagram is probably the most important thing which you have to learn about mirrors. And similar diagram for lenses. You will have to learn similar diagram for lenses. If you comprehended this diagram, you can always solve any problem concerning optical elements. Now, you probably noticed if you read the chapter that we have an equation which relates position of the object with position of the image, which is referred to as a mirror equation or a thin lens equation. Those equations come out exactly from geometrical analysis of the situation, and I want to illustrate it. So, for example, I use just 2 rays. Which 2 rays? This one is the shout. Chief ray, correct? So I use chief ray, and I use the, which one is that? The other one? Normal ray, to find the image of this point. Yes, I just got rid of the flower and left the point and its image. And now, whenever something is in front of the mirror, we assign a positive value for the position. This is just one component actually of position. So, and this is the only thing which we have to consider. The second one comes up automatically. So, S, which is position or X component of the position of the considered point with the origin at the mirror, is referred to as the position of the object. This one is position of the image. Recognize that it is only one component, and now we will relate those 2 components with the properties of the mirror, and look that we will just analyze geometrical relationships. So, for example, I can recognize that these 2 triangles are similar. Well, if they are similar, the ratios of corresponding sides are going to be equal. Now, if something is above the principal axis, I will assign positive value. So this value h is positive over here. Now, this value h is negative over here. It is like a y component of the position of the image and the object. And considering these 2 triangles, I can recognize that ratio of vertical component of the object to vertical component of the image. Actually, I took lengths. Now I'm taking lengths of these 2 sides. So since vertical component of the object here is a positive number, I have that the length of this side is just h. Now, vertical component of the image, of the position of the image, is negative, so the length of this side is minus that value. Right? So I take this ratio must be equal to the ratio of this side to this side. Now this side is equal to position of the object minus radius of curvature of the mirror. So I marked it here. And this side is equal to radius of curvature of the mirror minus position of the image. So considering these 2 similar triangles, I can write this proportion. I can write another proportion using these triangles. They are also similar. So this time, ratio of those two vertical components is equal to the ratio of these sides, this side and this side. So it is S over S prime. And, and actually, if you look at this, I mean, if you get rid of this H over H prime here, we have an equation which relates position of the object, position of the image, and the radius of curvature of the mirror. We already have a mirror equation. This is as good as the one which is in the book. It is just in a kind of not, I mean, I even don't know if this form is more complicated or not. But let's see that they are equivalent. So the rest is just algebra. Now, I multiply S, I mean numerator on the left-hand side by the denominator on the right-hand side. So I will have S times R minus S prime. And it is going to be equal to this product. So it is S prime minus S prime R. I got this expression. And now what did I do? I just grouped them together. So moved terms with have R on the left-hand side and put S prime on the right-hand side and combine those two. Now I'm going to divide everything by product, S prime and R. And I will get, so if I divide it by this by the product of all three, I will get 1 over S prime, which is, this is inverse of the position of the image. From this one, I will get inverse of the position of the object. And from here, I will have 2 divided by the radius of curvature of the mirror. Now, on the previous slide, I told you that that the focal point is halfway between the center of curvature and the mirror. So radius divided by 2 is equal to the distance of the focal point, or position of the focal point with respect to the mirror. That we refer to this position as the focal length of the mirror. All right. How about if we now if the mirror is concave, so it's a mirror like this one, we say that the focal length is positive and the focal point is in front of the mirror. If the curvature is, if the mirror surface is convex, so that the center of curvature is on the other side than the object. And do you know where you use a convex mirror? Anybody saw a convex mirror today? Robert did. Where did you see it? Right. Yes, we often use it on the right-hand side of our cars. Right, over there we have, and actually often on those mirrors it's written that the objects appear to be further away than they really are. We will see in a moment why it happens. Yeah, so those mirrors have center of curvature on the other side than the surface, and we assign a negative value for the radius of curvature and negative value for the focal length. Why don't we now do few exercises? So how about if I raise up the screen? And we will look for images. Now, how about, let's try to find out, let's say that I'll place a mirror at this location. Let's say focal point is here. So, oops. Center of curvature is going to be here. And let's say I take a object which is here. And let's find image of this point. So why don't you help me how to do it? So suggest which rays you want me to use. Kyle, which ray would you want me to use? Let's start with the chief ray. So chief ray is the ray which is from the object toward the point where the principal axis crosses the surface. Actually, whenever you draw the diagram, I advise you that you mark with a tiny arrow which way the ray, the light travels. So over here I will mark it this way. Now, you will be using probably a pen or a pencil, so you will not change color, so it can lead to confusion. The most common confusion which students have is to confuse which are object rays and which are image rays. I mean, for the first one, I will use different colors so that you don't confuse. But later on, I'm going to use with a just single pen and see how easy it is to confuse the rays. So chief ray is going to be object chief ray will be reflected as an image chief ray, and is going to be symmetrical. So usually I pick a symmetrical point of the object, mark over here, and draw a line from the center of the mirror where the principal axis crosses the mirror toward that point. And I mark that this light along this ray moves away from the mirror. All right, give me more hints. Yeah, because can I already locate the image? Where is the image? Oh, and can I? I need more information. All right, so we need to use another ray. Oh, and suggest another ray. Let's use the normal ray. So here is object normal ray. And how is it going to be reflected? Along the same line, right? Object normal ray after reflection becomes image normal ray. Can I already locate the image? Christy? Where? Where the two image rays cross, we will have the image of point O. Okay, so here is image of point O. Now, in order to have an image of entire arrow, I would actually need to repeat it for every point, construction for every point. But if you find just one, it's enough. It is that the plane of the image of of this object is going to be between the projection of that image point on the principal axis and that image point. So here we are going to have the image. Now, let's verify it. That it's the yes, Robert?
I must have missed what I was drawing. Why is there two arrows pointing at each other on the normal ray?
Because normal ray, yeah, we have to recognize where it hits the mirror. And what is this point? This point is the center of curvature of the sphere, right? So really, a line between the center and the surface of the sphere, what do we call the line between the center of the sphere and the surface? Well, I mean, or find out at what angle. I mean, imagine a sphere. Yeah, let's think. Right, it's a normal, right? Yeah, so really, if you think about entire surface, and this is point C. This is center of the sphere. So no matter how you draw the line, it is going to be a normal line. Now I take just fragment of it, right? So now the line hits at the angle of incidence is going to be 0 degrees. It's a normal incidence, right? Now, angle of incidence is supposed to be equal to angle of reflection. So which way the light is going to be reflected if it hits the surface at vertically? Exactly, go back, right? Do you understand why the normal ray? Yeah, because I mean I know what's the problem, because I didn't draw the curvature of the mirror. Correct. In principle, I should mark it like that. And in order to have center over here, this is how the curvature of the mirror would look like. Now this point and this point is a small error. So we don't have really to draw the surface. It is enough that we just use this straight line, which represents the surface of the mirror, the surface of the mirror. All right. Now let's do the other way. How about I want let's say that we use this, again, the same type of a mirror. So here I'll have focal point, center of the mirror. Oh, by the way, no, I didn't want to go. Now, how to verify that? Let's verify it. What rays should I use to verify that the construction is correct? Vincent. Which ray do you want me to use? Just give me a name. Parallel ray. See, I mean, he is good. Just say parallel ray. All right, I'll draw a parallel ray. Which parallel ray? The object parallel ray, correct. So let's use the object parallel ray. And object parallel ray, after reflection becomes, Vincent, it will become image, not parallel. Yes, Mike?
Focal.
Image focal. It will pass through the focal point. Well, so actually this construction confirms that the point which we found a moment ago was correct. Now, which ray is, I mean, we can still use the fourth one. Which one? Object focal ray. Let's use this too. And after reflection, it becomes image parallel. All right, so we see that indeed all four met at the same point. Let's make it a little bit shorter. And we have an image over here. Now look what will happen if you put your eye here. What would you think? Well, you would recognize that these rays are diverging from this point. Do you see that? You will think that this point is the source of those rays, and therefore you will interpret it as the point where the light is coming from. I will arrange actually this as a demonstration for tomorrow, so you will be able to see an object in front of a mirror. Really, you will have an impression that you can grab it. All right, let's now. How about what will happen if I put object here? So here, and consider this as the object. Why don't we draw a ray diagram and find out where is the image? Actually, you would recognize that it is one of common applications of a mirror, this configuration. So suggest me which ray to use. Eric, how about you? Which ray would you like to use?
We use the object focal.
Let's use object focal ray. All right, now, and I'm kind of confused at this point. How should I mark the arrow? Which way the light travels? To the right or to the left? What do you say? Okay. Anybody has other opinion? I mean, really, the light will travel that way. It is, however, useless. That light, the light coming out from this point and heading this way, will never interact with the mirror. It will never become an image ray. So that one is wrong. However, point emits light in all directions, so it also sends light in this direction. And this is the one which we have to use. That one is going to interact with the mirror. This light is not going to interact. So how about if I just mark it as a extension? I skipped point O. All right. Yes, so now this is a focal ray, although it doesn't pass, the light doesn't pass through the focal point, but the extension is. So you can imagine if you were shining a light from here, that light which passes through focal point has the mirror will be reflected in a particular way. What way? Parallel. It will become parallel after reflection. Okay, so we traced one ray. Give me a suggestion for another one. Would you like to give me a suggestion for a ray? Which one?
Object focal.
Let's use object focal. We have already used it. Chief ray. Okay, let's use chief ray. So chief ray will be a line from the object to the point where principal axis crosses the surface of the mirror, and it is going to be reflected symmetrically. So the light will travel this way. Can we already identify location of the image? Oscar says no, right? Can we or not? Brian says no. We need more rays, I think, right? Brian, this is your opinion. We need more rays. Give a suggestion which ray to use. Parallel. Which parallel? Object parallel. Okay, let's use object parallel ray. Object parallel ray. And it is going to be reflected as image focal ray. Correct. All right. Where is the image? Adam actually says that. Where is it? Behind the mirror. Yet look that those rays appears like they are coming from a point. However, the point is behind the mirror. So let me draw extensions of those rays. Yes, so they all appear to come from that point. Here is the image, and if I draw an entire arrow, this is the image of the arrow. Do you recall this configuration in real life? Christy, I bet you recall that configuration. When? When driving? In the right-hand side mirror, the objects are bigger. No, they are smaller. Actually, they are smaller. And I like what Adam just noticed. The image is larger than the object. Yeah, so we don't use this mirror in a car. Where? Well, glasses are not mirrors. Yes, Sam? In bathroom, right? Those magnifying mirrors. This is a magnifying mirror. If you gently want to pull out a particular hair from your eyebrows or make your lashes, then this is the type of a mirror you use. And now one more thing. Obviously, our conclusion is that Oscar and Brian were wrong, right? Brian, have you noticed that you were wrong? Yeah. Why? Because you could do it already when you had two rays. Yeah, the last ray which we drew was we started with object parallel ray. But having those two rays was enough. In principle, always having two rays is enough to produce an image. Well, let's now take a look at the side mirror. How the side mirror in a car produces an image. So we'll place an object in front of the mirror. However, the side mirror of the car is a convex mirror, so it has focal point on the other side. Let's say that focal point is here. So this is focal point, and twice that far is the center of curvature. So I can mark center of curvature over here. And give me a hint which ray to use to do the construction. Which one would you like to start with?
Chief ray.
Let's start with the chief ray. So here is object chief ray. Object chief ray is going to be reflected symmetrically. All right, another one. Let's use object parallel. And how about if I try to pull your leg now? It's going to be reflected as the image focal ray. Right? This is wrong. I told you that I'm going to pull your leg. What's wrong? It's in the wrong direction. Light will never get behind the mirror. It's going to be reflected in this direction so that the extension passes through the focal point. Can we locate the image? With two rays we should. So, Christy, where is it? It's also behind the mirror. I have to extend this chief ray. And here is the image. Yes, Robert?
So it's okay to say that as you get closer to a convex mirror, the image gets larger after you get past the focal point?
Oh,
And after you get past the center?
you mean when you change the curvature of the mirror, right?
When you change the curvature of the
Oh, you are moving. You are thinking about moving the object.
yes, as you get closer to the mirror on concave,
Right.
on a concave mirror, the image gets larger after you pass a certain point, right?
Well, we will come back to this tomorrow. Yeah, we will see what will happen if I put an object on the other side of a convex mirror. Now, how can I put an object on the other side of a convex mirror? In other words, actually, in general, how can I put an object behind the mirror? There's only one way to do it. You can never put your face behind the mirror, can you? So, but there is a way, actually, that I can put an object behind the mirror. What kind of object I would have to put? A what? A virtual object, correct. So I will have to use a lens or another mirror and create an image of the mirror behind the mirror. Then this image would become the object for the second mirror, and it would be a virtual object. All right. So see you tomorrow then.